Hello everyone and welcome back to the second week of CS 184. Today we're going to go over discussion 2A on transforms and texture mapping. So let's get started. So I'm only going to go through the questions, go through the lecture, watch the lecture videos. If you want to, really learn the concepts for the first time, that's the place to go. So let's go ahead and get started. The first section is about sampling. And the first question is, what is the connection between applying a box blur to an image and super sampling each pixel within the image? Okay, so if we recall, a box blur looks a little something like this, where we have a grid, and each of these samples is individually going to be weighted, in this case 1/9. And so essentially what you're doing is you're just averaging all the values over this grid and then setting that as the new value. So if we were to take one of these box blurs, make it the size of a pixel. So this whole thing, this is 1 pixel. 1 pixel, whoops. 1 pixel, okay. And if we were to then, let's say we just had an x by x, or an x by x, 1 pixel box blur. So essentially within 1 pixel we have x grid spots in one dimension, x in the other, so x squared total. Then essentially what we're doing is we're breaking this pixel up into a bunch of smaller chunks, averaging them all together, and setting that as a new value for the pixel. But that's exactly what super sampling each pixel within the image is. We break it up into smaller chunks, sample at a higher rate, and then average. So essentially a 1 pixel sized box blur with x of dimensions x by x is the same thing as super sampling with a super sample rate of x by x. Okay, so that's the first one. The 1 pixel box blur is the same as super sampling. So let's keep going. The next one, so we have two wheels that rotate at different speeds with different number of spokes that we want to record with our camera. Wheel A has 4 spokes and rotates at a rate of 6 rotations per second. Wheel B has 6 spokes and rotates at a rate of 5 rotations per second. Okay, so let's start by looking at wheel A. It has 4 spokes, so that means within 1 rotation, it's going to look the exact same 4 times, right? And if this doesn't make sense to you, maybe try drawing it and clear it up. So it's going to look the exact same 4 times in 1 rotation. And now let's remember that when we talk about frequency, what we're talking about is hertz. And the units of hertz is 1/seconds. Basically, how many times does something happen per second? And so in this case, we're interested in how many times does this wheel look the exact same per second, right? Because that will tell us how often we need to sample to make sure we see everything. So in this case, wheel A has 4 spokes, so it looks the same 4 times per rotation, and it's going through 24 rotations per second. So what that tells us is it's going to look the exact same 24 times per second. So wheel A is rotating at a frequency of 24 hertz. Okay, now let's look at wheel B. Wheel B has 6 spokes, so per rotation it's going to look the exact same 6 times, and it rotates at a rate of 5 rotations per second. So that means per second we have 5 rotations, and 6 times it looks the same per rotation. So that's going to be 30 hertz, right? Because 30 times a second we're going to look the exact same. So now we want to know, what is the lowest integer frame rate in frames per second we need on our camera to avoid any aliasing effects? So if you look at the lecture, we discussed an idea called the Nyquist frequency. And what the Nyquist theorem tells us is that the Nyquist frequency is the lowest frequency we need to sample at to avoid aliasing effects. And that is a frequency higher than double the max frequency. Okay, so if I write that down, Nyquist is equal to, or we say greater than 2x max frequency. Okay, so in this case, if we look at both A and B, we see that 30 hertz is our max frequency. So now we need a frequency greater than twice that. So, and since we want integer frequency, we're going to go 30 times 2, 60, and then we have to go greater, so it's going to be 61 hertz, or 61 frames per second. Okay, so there we go. That's our answer. Okay, let's keep going. So now we're going to talk about some basic transforms. So, which of the following transforms preserves the distances between every pair of points on an object? And the options are rotation, translation, scaling, reflection, and shearing. So here I've gone ahead and drawn a few examples of these transforms. I'm sorry they're not the greatest pictures, but I hope they can get the idea across. So let's just go from left to right one by one and see which of these preserves the distances between every point on the object. Okay? So first off, we have rotation on the left. So this red square is a rotated version of the original black square. But the thing is, we've only taken the exact same shape and tilted it, moved it around an axis, but we haven't actually changed any of the side lengths, which may not be 100% clear in this picture, but I hope you can kind of tell that that's the case. And so what we're gonna get is that rotation does not change the distances between every pair of points. Sorry. So rotation, it counts. Okay. Next up is translation. So all translation is taking an object from one spot and just shifting it over to another spot. We don't change it, nothing. We just move it. So translation also is going to preserve the distances between every pair of points, since we're just taking the exact same shape and just moving it to a new location, like we did with this red square from that black square. So translation, also good. Now let's look at scaling. So in this picture for scaling, we've taken this small black square, whose top is kind of covered, and replaced it with this larger red rectangle. So in this case, I think quite trivially you can see that it did not preserve the distances between every pair of points, because this side is now double the length of before. So scaling, nope. Now let's look at reflection. So this black square is reflected onto this red square. And so the red square, it still has the exact same. We've essentially just taken every x value and flipped it. So positive became negative. But that still doesn't change the distances between every pair of objects. So that means that reflection also satisfies this property. And now let's look at the last one, shearing. So what shearing is essentially is it's kind of like tilting the cube. So as you can see here, there's a little black square in the back, and then we shear it. So we take its two vertical legs and we tilt them by the same angle. And I think you can also see quite trivially here that the distances between every pair of points is not the same, because the side lengths of this red square, not even a square, parallelogram, are longer than the side lengths of the original black square. So shearing does not satisfy this property. So of all these transforms, rotation, translation, and reflection do satisfy this property, and scaling and shearing don't. And now what this also means is that any combination of rotation, translation, and reflection will still preserve the distance between every pair of points on the object, okay? But if we include any scaling or shearing, we can't guarantee that. Okay, let's keep going. So now, number 2, write the transformation matrix for a 30 degrees counterclockwise rotation, assuming homogeneous coordinates in 2D. Okay, so what I've written on the left here is the rotation matrix, and I'm not going to go into the derivation of this matrix right now, but if you are interested in that, go through the lecture slides, and there's a great picture in there that kind of explains how this matrix is derived. And if that's not clear, you can also look it up online. There's plenty of good examples of how that works. So let's go ahead and write this matrix. Now the first thing to notice is that it says assuming homogeneous coordinates in 2D. So that means that since we're talking about homogeneous coordinates in 2D, we're going to have a 3 by 3 matrix as our transformation matrix, okay? So let's go ahead and make the brackets. Okay, now the first thing we can say about this matrix is it's only rotation, 30 degrees counterclockwise rotation. There's no translation, which means that the rightmost column, we can go ahead and put 0, 0, 1, right? Because this column is used for translation with the homogeneous transformation. Now another thing we can do is remember that we're talking in 2D. So this third row is representing either, it has either a 0 or a 1 telling us whether it's a point or a vector. And now both of these transformations, both of these first two columns are going to have zeros here. So 0, 0. Okay, so now we have the bottom row and the last column done. And now we want to put in these remaining 4 values. So what are these going to be? Well, let's just take our rotation matrix and plug in 30 degrees and see what we get. Okay, so first up in this top left corner, we're going to have cosine of theta, cosine of 30. And, I'm not going to go through the math right now, but just, you can check out a unit circle. But that's going to be root 3 over 2. Okay, that was really messed up. Root 3 over 2. Okay, sorry that took so long. Now we're going to want to go negative sine theta. So sine of 30 degrees is a half, but we want to do negative. So it's going to be negative 1 over 2. Now it's going to be just sine theta, so that's just going to be 1 over 2. And then cosine theta, which is the same as above, so root 3 over 2. Okay? And that is our answer right there. And there we go. Okay? And actually, let me erase this. Let me go ahead and fix this just because it's a little... Not sure what's going on with my iPad. Sorry about that. Okay, there we go. That should do it. So there's our transformation matrix for 30 degrees counterclockwise rotation in homogeneous coordinates. So let's keep going. Number 3, write the transformation matrix for a 2D object that is reflected across the y-axis, then translated up by 1 unit, to the right by 3 units, then rotated around the origin by 90 degrees counterclockwise. And leaving it as a product of matrices is fine. Okay. So the first thing we should do in this is figure out how many matrices are we going to need, right? So if we look through the problem, we see that we're applying 3 different transformations. We're reflecting across the y-axis, then we're translating up by 1 to the right by 3, and those can both be done in one thanks to homogeneous transformations. And then we're rotating around the origin by 90 degrees counterclockwise. And so that's going to be another matrix, similar to what we just did in number 2. Okay, so let's start this problem just by writing some placeholders. Right, we have our 3 matrices that we're going to multiply together. And now here's a key thing. When we're composing transformations like we are in this case, we have 3 different transformations and we're putting them all together. Order matters. Order is really important in this case. And the way it works is we multiply right to left. So this rightmost matrix is our first transformation, then the middle is our second, and then the leftmost is our last transformation. So in this case, this one is going to be the reflection. This one is going to be translate, and then this one is going to be rotate. Okay? So that's the order these matrices are going to be in, because that's the order we're transforming our 2D object in. So first of all, let's go ahead and start with the reflect matrix. Now we're not doing any translation here, so we can quickly fill in this last column as 0, 0, 1. And now for the rest of the matrix, all we want to do is take it, reflect across the y-axis. So we take the x coordinate of a point and flip it, make it negative, and leave the y totally alone, right? And so the way we're going to do that is, and you can also see an example of this on the lecture slides. I think there's an example of, a reflection matrix. And that's just going to look like -1, 0, 0, 1, 0, 0, okay? So every x coordinate is going to get, we're going to flip the sign on the x, leave the y as they are, and that's going to reflect around the y-axis. Now, let's move on to the next one, so translation. We want to translate up by 1 unit and to the right by 3 units, and not do anything else, okay? So now what this lets us do is fill in this side first. And so, 1, 0, 0, 1, basically just the identity matrix, because we don't want to do anything in terms of rotating, reflecting, none of that. But what is interesting is this last column, because that's where translation happens on these homogeneous matrices. And so we want to go up by 1 unit and to the right by 3. So in the x direction, we want to put a 3, and in the y, we want to put a 1, and then a 0 here. Oh, whoops, sorry, that should be a 1. Okay, and so there we go. That's our, let me rewrite this. Okay, so there we go. That's our translation matrix. Now let's come over to rotate. So we can look back at number 2, and essentially it's going to be very much of the similar things, just with different numbers. So we can go ahead and fill this in, 0, 0, 1, 0, 0. Okay, now cosine of 90. Cosine of 90 is 0. Sine of 90 is 1, so -1, 1, 0. Okay, and there we go. We have our matrices. Rotate, translate, reflect. They're in the right order because we want to do reflection first, then translation, then rotation. And that's your answer. If you want to multiply it out, you absolutely can. You'll get another 3 by 3 matrix that will have, the combination of these, but it's perfectly fine to leave it like this also. Okay, so let's keep going. So next up, now we're going to talk about texture mapping. So one of the pretty key tools that we use throughout this class, not just in texture mapping, is barycentric coordinates. And so barycentric coordinates are essentially a special coordinate system to locate points within a triangle relative to its vertices. So barycentric coordinates are 3 coordinates. It's an alpha, beta, and gamma value, and they can be thought of as weights being assigned to the vertex. So the position of the point, so if you look at this equation right down there, the position xy is equal to essentially a weighted sum of the 3 vertices of the triangle, and alpha, beta, and gamma tell us how much to weight each of these points. And so if you look at this diagram I've drawn on the right here, it gives you a little bit more of an idea of how we actually get alpha, beta, and gamma. So the point we want to represent in barycentric coordinates is that red dot right there. And this longer dashed line is essentially the perpendicular. If we drop a perpendicular from A to the side across it, that's that line. And then what we do is we find how far along that line is this red point. And that is our alpha value, as I've labeled right here, which I can highlight. So right there, that's our alpha value. Okay, and then we do the same thing for B. We drop a perpendicular to the side opposite that. See how far the red dot is on that line. Same with C. And that's how we'll get alpha, beta, and gamma. Now, one really important thing to keep in mind is for valid barycentric coordinates, there's always one equation that holds true. And that is, I'm going to put it right here, alpha plus beta plus gamma is equal to 1. Okay? So the total weighted average has to add up to 1. Okay, so now let's look at this first question. What happens if alpha, beta, or gamma is less than 0? Well, so we looked over here in our drawing, we have a value for alpha. So how would this value of alpha be less than 0? And the answer is, well, what if this point was instead here? Then if we do the same exact calculations we just did, right? We could drop that down. This would come out here. And now this would be our alpha value, which would be negative because we are beyond the opposite side relative to A. So essentially what that's telling us is if alpha, beta, or gamma is less than 0, that means our point is outside the triangle. So I can go ahead and write this down. Point is outside the triangle. Okay. However, as long as this equation still holds, alpha plus beta plus gamma equals 1, it's still going to be in the same plane as this triangle. Okay, so if any of them are less than 0, it's outside, but as long as this constraint holds, they're still on the same plane. So just keep that in mind. Okay, let's keep going. So now the question is, what is the barycentric coordinate of the point corresponding to the screen space coordinates x, y is equal to 3/4, 1/4 in the following diagram? Okay, so let's take a look here. As we talked about up here, it's basically telling us that xy is this weighted sum of a, b, and c, right? So we can come down here and let's write some equations of what we know. So the first thing we know, and this is a given, like we just talked about, is alpha plus beta plus gamma is equal to 1. Okay? Right off the bat, that's always a known. And then now we can say, well, so the x-coordinate is a weighted average of the x-coordinates of a, b, and c. So we can write that x, or 3/4, is equal to alpha times 0, right? Because the x value of a is 0, plus beta times 1, because the x value of b is 1, plus gamma times 1, because the x value of c is 1. Okay? And now we can write one more equation, this time for y. So 1/2 is equal to alpha times 0, plus beta times 1, plus gamma times 0. Okay? So now, right off the bat, with this last equation here, we can go ahead and tell beta is equal to 1/2, right? And well, now that we know that beta is equal to 1/2, we can take this equation and rewrite it over here. So 3/4 is equal to 1/2 plus gamma times 1. And so if we subtract 1/2 from both sides, we get gamma is equal to 1/4. Okay, well now we have two values, and we have this last equation of them all summing up to 1. So let's plug these into that. So we're going to go alpha plus 1/2 plus 1/4 is equal to 1. Subtract from both sides, and we get alpha is equal to 1/4. Okay, and there we go. These are our answers. So beta is equal to 1/2, alpha is equal to 1/4, and gamma is equal to 1/4. And those are our barycentric coordinates. They add up to 1, and the math checks out. Okay, so that's all. We just write out the equations. We have 3 unknowns, and we have 3 equations, so we're able to solve and get our answer. So let's keep going. So now, suppose we specify the colors at each of the vertices in order to color the triangle. If the RGB values of A, B, C are 1, 0, 0, 0, 1, 0, and 0, 0, 1, then what is the interpolated color at the selected point above? Okay, so now we have the barycentric coordinates, so finding the color is not that difficult. All we want to do is alpha times A plus beta times B, put parentheses, and gamma times C. Okay, which is just going to be 1/4 times A plus 1/2 times B plus 1/4 times C. And so if we look at the actual values, you'll notice that, A has 1 in the first spot, B has 1 in the second, C has 1 in the top. There's no overlap. And so we can kind of quickly rewrite this as the A is going to contribute the 1/4 there, 1/2, and 1/4. Just like that, right? So it's just going to be a weighted combination of A, B, and C based on our barycentric coordinates, and we get our answer. Nice and easy. Okay. So once we have the barycentric coordinates, here we were using it for an actual position, but we can also just use them just as easily for a color. Okay, let's keep going. So the next topic is texture coordinates and MIP maps. Okay, so now that we have these barycentric coordinates, and we've seen we can use them for position, we can use them for color, you can also use them for texture space coordinates. So if we know what the coordinates in texture space are for A, B, and C, the corners of the triangle, we can use the barycentric weights to essentially interpolate between them and find the texture coordinates of any position, any point on that triangle, using this equation right here, right? So, however, it's not perfect. We don't always get a pixel directly on a texel. So a pixel may cover a larger area or a smaller area. And when this happens, we essentially get aliasing. We get jaggies, we get pictures that don't look as good when we render them. And so one way to do this is filtering, but that's kind of computationally intense. So another idea is we store it in a form of a MIP map. And what a MIP map is there's a base level of highest resolution and then subsequent level with lower and lower resolutions. So essentially, if we find that one pixel covers many texels, we'll instead just get a higher resolution map and use that in place. And so I'm not going to go into too many details on this here. Go to the lecture, watch the videos, and you'll be able to learn all about MIP maps there. So I'm just going to go through some of these questions and see if we can work through them. So the first question is, the resolution of a MIP map at level 3 is what fraction of the size of the original texture? Okay, so let's start. So the base level of a MIP map is level 0. Okay, and this is going to be, let's say, x by x dimensions, right? And if we do the math, so the total size of this is going to be x squared, right? Straightforward enough. Now the next level, level 1, is going to be half in each dimension. So it's going to be x by x over 2 x over 2 by x over 2. And so if we, square that, we're going to get x squared over 4. And so now if we continue this similar logic, we'll realize that the third level is going to be x over 8 by x over 8. Essentially, we're 8 times smaller in each dimension. And so if we find the total area of this, we're going to get x squared over 64. Okay, so here's the resolution at level 3, and here's the original one. So as you can see, the resolution at the level 3 is 64 times smaller, or the fraction is 1 over 64. And so that's our answer. Okay, and if we had, if the question had asked what's level 1, it would have been 4 times. If it was level 2, it would have been 16 times, and so on and so forth. Okay? So, now that we know that, let's move on to number 2, which is related, and ask, a MIP map takes up what fraction of the original map's size in memory? Right? So, right here in problem 1, we saw the first level took x squared, second one took 1/4 that, then 1/16, then 1/64. And so, if you think about this, we can write this out as an infinite series, right? So we can say we want to find the total space. So we're going to sum up over all of them from the first level, so k equals 0, all the way to infinity, assuming, we keep infinite maps. And so I'm going to say that the original size is a, and for every level, it's going to decrease by 1/4, right? So when the first level is 0, it's just going to be a. Next one, it's going to be 1/4 the size. Next 1/16, next 1/64, all the way down. Okay, and so now to actually solve this, we can just use the formula, which tells us that the sum of an infinite series is the first value, so a, over 1 minus r, where r is kind of the I don't know what to call it, the number you multiply every time. So in this case, r is 1/4, and a is a. So if we plug this in, we get a over 1 minus 1/4. And if we write that out, that's 4/3 a. So essentially, storing the entire mipmap takes up 4/3 as much space as the original texture map in memory. Okay? And that's our answer, 4/3. Okay. And so now, let's talk about the next thing. So how do we determine which level of a mipmap to use for a particular screen space pixel x, y? Okay, so first of all, on the left here, I've written out some conversions. So we have the first pixel, x, y, right here. And that translates to some UV coordinates in the texture space, 0, 0. We're going to call it T0. And then we have, if we move one pixel over in the x dimension, so x plus 1, but y stays the same, that's going to result in some new UV coordinates, which we're going to call T1. And then the last one, which is, I messed up writing, if we stay the same in the x dimension, but move over one pixel in y, that's going to result in some new coordinates that let's call T2. Okay? So essentially, we've moved one pixel in x, one pixel in y, and we've calculated the new texture coordinates. Now what we're going to do is we're going to calculate some values, which is going to look like this. So du dx and dv dx. So essentially, how much are v and u changing when we move in the x direction is going to be equal to T1 minus T0. Okay? And so the reason we can say this is because between T1 and T0, we moved one pixel in the x direction. And then we saw what the resulting texture coordinates were. So when we subtract, we see that's the difference in texture coordinates from moving in the x direction. And then we can write a similar thing, du dy and dv dy, except this time we're going to go T2 minus T0, because for T2 we moved one pixel in the y direction but kept the x the same. Okay, so now that we have these two vectors, we have how much the UV coordinates change moving in x and how much we move in y. What we want to find is which one of these do we move more in. So what we're going to do is, let me demarcate that, okay? And then we're going to go L, we're going to call L, is equal to the max of dx and dy. Okay, so I kind of used a little bit of a short form here. I'm sorry about that. I just don't have a lot of space to work with. But dx essentially is this vector over here, du dx, and dy is this vector over here, du dy, and dv dy. So essentially, and these brackets are, if you watch the math intro discussion, that's the length of the vector. So essentially, we're going to square each of these components, add it together, take the square root. And so what we're doing in this max operation is we're basically saying, if I move in the x or I move in the y, in which direction are my texture coordinates changing the fastest, right? We want to find which of the two, whether x or y, represents the biggest change in the x direction, texture coordinate space, so that we can make sure to get the right-sized mipmap values. And so in order to get from this L value to the actual level of the mipmap, which is going to be D, we're just going to do D is equal to log base 2 of L. Okay? And so that's the final step. So what we did is we moved one pixel in the X, one pixel in the Y, see how much that moved us in texture space. Then we calculated which one is greater, which movement is greater, and then use that to pick our level so that we're not getting any aliasing effects. Okay, so there's more detail on this. I'm sorry it's a little cramped, but there's more detail on this in the slides in the lecture. So, watch that, check out those slides. That should be able to help a little more. Okay, and now let's talk about the last question. So how can we combine values from two neighboring mipmap levels, and why would we want to do that? Okay, so one thing we could do, well, we've talked a lot about, well, not a lot, we talked a little bit about interpolation. I think you guys went over, bilinear interpolation in class, where if a point is not directly on a pixel, you can kind of take the values nearby and then do a weighted average to see what value you should give that point. And so we can do a similar thing between mipmap levels. So when we calculate this D value, we can kind of see how far is it from each of the two mipmap levels, and then use that to do a weighted average of what of the different colors that the mipmaps will give you. And so what this is called trilinear filtering. Okay, and the reason we want to do this is because otherwise if two different pixels use different mipmap levels, it can look kind of abrupt. And so we instead do this to make the transition smoother and make our pictures look a little nicer. Okay, so that's all for today's discussion. We went over a little bit of texture mapping, some barycentric coordinates, and some basic transforms and sampling. And I'll see you guys on Thursday.